So Luigi, in the last episode we looked at the difference between high level languages like BASIC and Python and low level languages like Zilog and Moss, where you actually use binary essentially. We're going to look at an example of assembly language which sits in the middle, and we use hexadecimal to code. So we're going to jump straight over to the Commodore 64 and we're going to load up an application called Supermon, which will allow us to actually get close to the metal, as they say, and program at a assembly language level. So here we go. It looks like we're still in BASIC because it says Commodore BASIC at the top, but if we try and type basic commands now, such as print hi, we get a question mark error because we're no longer in BASIC, so the computer doesn't understand anymore. So if I type R, enter, just to bring up the stuff that's above, we're now in the CPU, and we can see what the different registers in the CPU have in them. So the PC is the program counter, there's SR, there's AC, XR. These are different bits of memory within the CPU, and we don't need to understand too much about what they're all for at the moment. If we look at the accumulator, which is AC, what value would you say is currently held in the accumulator?
40.
40, yeah, it looks like 40, doesn't it? But actually this is not a decimal number, this is a hexadecimal number. And the way hexadecimal works is that your units don't go up to 9 before you add another number to the left. That's decimal. Yeah, so if you go up to 9, then you add a 1 on the left hand side and it becomes 10, and then you go up to 19 and then it becomes 20. Hexadecimal, you actually go up to 16 before you add a number to the left. And the way that you do that is you count 0, 1, 2 all the way up to 9, and then you count A, B, C, D, E, F, and then you add a 1 to the number on the left hand side. Okay? So that's why we call it hexadecimal, as in 6 decimal, because it's counting through 16. Okay? And that's why you can actually see the number F6 in the stack pointer, which is the entry on the right hand side. Okay? Yeah. But it could have easily been 6F, that would also make sense. Sounds a bit strange, but people who program get used to this quite quickly. All right? The reason we have this system is that each of these 2-digit numbers represents 1 byte of data. And each individual number, so the 4 and the 0, for example, they represent nibbles. So a nibble is half a byte. Yeah, I know someone was having a joke when they came up with that. But when you see 40, it's actually going to be 64 in decimal, because it's 4 times 16 plus 0. That's 2 nibbles. And the reason we have nibbles is that if you've got 4 binary digits, 0101 or 1001 or any combination, there's actually 16 different combinations that you can come up with 4 binary digits. And therefore you can express a nibble as a number from 0 up to F in the way we just described. Okay? Does that make sense?
Yeah.
Yeah? Good. So we've got values in there at the moment, and we know that we've got RAM locations, and the RAM locations can also be expressed as hexadecimal, but it's a 16, if you remember we had 16 bits as a memory address, so therefore you'd have 4 nibbles. So what we're going to do is we're going to have a look at what's stored in a certain location in this computer at the moment. So by typing in M for memory and looking at the location 0380, not to be confused with 380 because this is a hexadecimal number, you can see that there's lots and lots of empty bytes here. Okay, 0380 is 00. 0381 is also 00, and you can see that on each line you get 8 bytes, and then it tells you that the next row starts at location 0388 in RAM, and that's all 0 as well. This is great because we want to use this for a little test on machine language. So we're going to actually, what we can do here is manually update what's in each byte. So I'm going to put 11 and 99 in these 2 bytes of data. I'm going to press enter, and they're there now. Okay, if I type M0380 to check, it should. There they are. So I've now updated those bytes of data. Is that making sense so far?
Yeah.
Good. Now what I'm going to do is I'm going to write myself a little program in assembly. And I happen to know that I can use what's called the tape cassette buffer in Commodore 64 to write short programs. So I'm going to actually start at location 033C to write a program. And I've done that a little bit wrong. I'm no expert on this, you know. It's going to take me a little while to get used to it. I have to type in A for assemble. Otherwise it will think I'm writing directly into machine language rather than assembly. Now what I'm going to do is I'm going to load the accumulator in the CPU with this mnemonic or instruction. So I'm saying load accumulator with the value that's in 0380. Which value is that in 0380 at the moment?
That is the 1199.
Well, 11 is 0380. That's one byte.
Okay.
Yeah, if I went to 0381, that would be the 99.
Oh yeah.
So it's it's actually translated that into machine language. So where it says AD8003, that's actually the opcode for load into the accumulator. And then 8003 is the same as 0380, but it switches the high byte and the low byte around in machine code. My next instruction is I want to load the X register in the CPU. I want to load with 0381, which is where we held the other value. So I've now loaded my values into the CPU, or at least I will do if I run the program. Make sense?
Yeah.
So I'm now going to run the program. I'm going to go to 033C. This is how we ask the program to run. I'm going to press enter. Would you look at that? So now it's showing us our CPU again, and we've loaded 11 into the accumulator. Oh no, we haven't. Correct yourself, Link. We've loaded 11 because this is hexadecimal into the accumulator, and we've loaded 99 into the X register. Okay. Now I'm going to write a program again. So I'm going to start again. I want to, in 033C, I want to store the accumulator I'm panicking. To store the accumulator into 0381. And then I want to store what's in the X register into 0380. And then I'm going to run that. I'm going to go to 033C. Okay, notice that what's in the accumulator in the X register hasn't changed because that's just what I loaded in there before. So that's still in there. But now if I go to 0380, we should see that the 11 and the 99 have now switched places. So I brought both values into different locations within the CPU, and then I sent them back into the different location that they weren't in previously, so they've swapped places within RAM. I get that that's not the most exciting thing in the world, right? But what I want you to understand is that what we've done there is hugely efficient. If you asked BASIC to do that, and then you had a look at the code that BASIC had to run through to do that, it would be much, much longer than the simple instructions that we put into the Commodore in order to achieve it in machine language. So that's just a simple introduction to hexadecimal and machine language. All right, any thoughts?
Well, it's very difficult. That's the main thought that comes to mind. It looks very, very difficult.
Yes, that's a really interesting point. And what Jim says, who wrote the book on machine language, he says that if you take people who learn machine language first and then show them BASIC, they find it much harder to transition to BASIC. They'll complain that BASIC doesn't really make sense. Whereas if somebody has learnt BASIC and then you reveal to them that machine language is available, normally they're grateful and go, oh wow, this is so much simpler and makes so much more sense, and I can get much more power from my computer with it. Yeah. So it's just about learning to think like a computer, and then you can program at speed. All right?
Yeah.
Fantastic. Good. Well done. I know that's hard, but it's something I thought
Yeah.
was useful to teach you. All right, good.